Because remember, well, there's proteins that hide these things on purpose. We're talking now about mutation, changes that always lead to the destruction of a splice acceptor or a splice donor. Is that satisfactory?
Yeah, so it just wouldn't even cut that second splice that we're saying.
I think, yeah, I think
Because it's preoccupied with the first one. So.
yeah, it's looking for a splice acceptor specifically at that point. So I think my prediction is we would skip that exon. And you just get to say that. What's wrong with the transcript? It's too short. That certainly is true. We can be more descriptive. It's too short because we will have skipped an exon. See the diagram and you'll see what I mean. Whereas the answer was different for a missing splice donor. We said we are retaining an intron. The transcript is too long. And then there's consequences that we can detail or at least hypothesize for the protein as well. Ribosome binding site defects. I think, just like when you read this question, it had to be a eukaryotic gene that we were thinking about. Now when it says ribosome binding site defects, I think that has to be a prokaryotic transcript that we're talking about. If there is a defective Shine-Dalgarno. So again, we can think about a polycistronic prokaryotic transcript. Should be a Shine-Dalgarno, Shine-Dalgarno, Shine-Dalgarno. So that'll never be confused with splice donor, right? Because it's a whole different kind of organism. So we're supposed to jump on, translate, fall off. Jump on, translate, fall off. Jump on, translate, fall off. If there is a defect in this, this will never be translated. We'll translate this one, we'll translate that one, we'll never translate this one. So what's wrong with the transcript? Well, there's nothing wrong with the transcript, basically, except for that mutation itself. Transcript's not too big, transcript's not too small. What's wrong with the protein product? Well, we're missing an entire protein product. If the ribosome can't enter, it can't give us that. And as we said, if prokaryotic genes are organized because we need protein 1, 2, and 3 all at the same time, or we can't do job 1, making protein 2 and 3 doesn't do us any good. These are organized in an operon because we need them all, so we're kind of in bad shape. Polyadenylation signal. Now we know we're definitely talking about a eukaryote, right? If that AAUAAA was missing, now our transcript would be too long, because I guess we would have to cruise on until we accidentally bumped into another AAUAAA. How often is that going to happen? That's a 6-base sequence. How often do we expect to find any particular 6-base sequence? 1 out of 4,096. See how this all sort of comes around. This is all stuff we've talked about before. So what's the effect of a defect that ruins a polyadenylation signal? My transcript will be too long. Does that have any effect at all on the protein? No, the protein's perfect. We jump on, we translate, we jump off. Poly A tail is way the heck down the street. I don't care if it's 2 miles down the street as opposed to 1 mile down the street. I translated my entire product. So as you go through this list of things that we know about, you can see how the effect on the transcript, the effect on the protein, you're really revealing that you know what these do. Are they transcription signals? Are they translation signals? Do you know the difference between RNA and protein? Of course we do, but these questions are certainly challenging, and they make you hypothesize, so that's all good scientific stuff. I guess I don't see you again until Wednesday.
Yeah, so the polydenylation